This is a higher tier video. That means students studying combined science and those studying separate science need to watch this video if they are studying higher tier. We are going to be looking at conservation of momentum. We will recall the equation and units for momentum, explain the meaning of the words conservation of momentum, and perform calculations involving collisions using the principle of conservation of momentum. There will be some multiple choice questions and also some calculations questions for you to try, so you will need a pen and paper and also a calculator. If you don't have these on you, please pause the video and get them now. Let's start with recalling the equation and units for momentum. So momentum is a property that only involves moving objects. Momentum is a measure of how hard it is to change an object's motion. Of both of these objects, the lorry has a greater mass. If both are travelling at the same velocity, the lorry will have a greater momentum. In this example, the hare will have a greater velocity. If both the tortoise and the hare have the same mass, then the hare will have the greater momentum. Momentum is defined by this equation. Momentum equals mass times velocity. The units for mass are kilograms, the units for velocity are meters per second, and therefore the units for momentum are kilogram meters per second. We use the symbol P to represent momentum, so if you want to write this equation as symbols, you would write P equals mv. Can you now pause this video and answer multiple choice questions 1, 2, and 3? You should now have A, B, C, or D written down for questions 1, 2, and 3. So question number 1, momentum is affected by, should be mass and velocity. Question number 2, momentum equals mass times by velocity. And question number 3, the units for momentum are kilograms meters per second. So let's now have a look at an example together. Calculate the momentum of an object if its velocity is 76 meters per second and its mass is 80 kilograms. So we first need to identify the variables in the question. The velocity, which is symbol v, is 76 meters per second, and the mass, which we're writing as a symbol m, is 80 kilograms. Next, we need to check our units. The units for velocity are meters per second, so they don't need to be converted. And the units for mass are kilograms, so they don't need to be converted. Step 3, we write out the equation in words or symbols. So here the relevant equation is momentum is mass times velocity. More often than not, we'll write as P equals mv. Step 4, substitute the numbers. So we need to substitute 80 for the mass and 76 for the velocity. And then finally, step 5, we transform the equation if needed. In this case, we don't need to transform our equation because momentum is already the subject. And finally, we calculate the answer and write it with units. So we should end up with 6,080 kilograms meters per second. So now we're going to look at another example, and you're going to complete this one by yourself. You are going to calculate the momentum of a 65 kilogram person running at 3.5 meters per second. I'm going to put the different steps up that you need, but you are now going to pause the video and perform the calculation by yourself. So let's now self-assess our answers. So firstly, we had to identify our variables. You should have written m as 65 and v is 3.5 meters per second. We then had to check our units. The mass needs to be in kilograms, so that is correct. And the velocity needs to be in meters per second, which is also correct. We then write out the equation in words or symbols, so you should have written down P equals mv. We then substitute in the numbers, so we should have written 65 times 3.5. We don't need to transform the equation, we just need to write our answer with units, so we should have got 227.5 and the units as kilograms meters per second. We have recalled the equation in units for momentum. We are now going to explain the meaning conservation of momentum. In this diagram, we can see two people. We can see that the England player is running forwards or towards us, and the All Black player is running backwards. Since momentum is mass times by velocity, mass is a scalar quantity, but velocity is a vector. And that means momentum is also a vector quantity. So the fact that we've got one player moving forward and one moving backwards is an important point. Because the England player is moving forwards, we would assign a positive value to the velocity and therefore also to the momentum. And the All Blacks player is moving backwards and so moving in the opposite direction, so we would assign a negative value to the velocity and therefore the momentum would also have a negative sign. The principle of conservation of momentum states this. In a closed system, the total momentum before an event is equal to the total momentum after. We can look at this example and see that the conservation of momentum is being obeyed. At the start, the person and the ball are both stationary, meaning the total momentum is 0. We know that because neither of them are moving. The momentum at the end is still 0 because the cart and the person are moving in opposite directions. Therefore, they have opposite velocities and their momentum will also be opposite. Can we now pause our video and answer questions 4 and 5? Good, so you should now have A, B, C or D written down for questions 4 and 5. So number 4, momentum before an event and after event is always the same. That is the principle of conservation of momentum. And number 5, the conservation of momentum applies for closed systems. So let's now move on to the final part of this video. We need to perform calculations involving collisions using the principle of conservation of momentum. Before we start the calculations, we have to make sure that we have the correct notation. We use the symbol U for the initial velocity. When we say initial velocity, we mean the velocity at the start. And we use the symbol V for the final velocity, that is the velocity at the end. Since velocity is a vector, any motion in the forward direction we are going to write with a plus sign, and any motion in the backwards direction we are going to write with a negative sign. So how does this manifest itself into a question? Let's have a look at this example. The diagram shows two supermarket trolleys moving in the same direction. Trolley A is full of shopping and has a total mass of 8 kilograms and is moving at 2 meters per second. Trolley B is empty and has a mass of 4 kilograms and is moving at a velocity of 0.5 meters per second. We want to first calculate the momentum of both Trolley A and Trolley B, and then we want to answer part 2, which tells us that the trolleys in the diagram collide and join together, they move off together, and we want to calculate the velocity with which they move off together. So let's start with part 1. Calculate the momentum of both Trolley A and Trolley B. So starting with Trolley A. The mass of Trolley A, and you can see I've used a subscript A here to make sure that we know which mass we are talking about, is 8 kilograms. And the velocity of Trolley B is 2 meters per second. Note how I've used a U here instead of a V. That is because it is the velocity at the start, that initial velocity. We then write our normal 3 lines of working, the equation in symbol form. So we know that momentum is mass times velocity. And so here we're using P equals mu because U is the initial velocity. And we substitute in our numbers and we get 16 kilograms meters per second. We then do the same for Trolley B. So the mass of Trolley B is 4 kilograms. The initial velocity of Trolley B is 0.5 meters per second. And then we perform our 3 lines of working and we find out that the momentum of Trolley B is 2 kilograms meters per second. So I've just written those answers for part 1 up at the top so that we've got enough space for part 2. So the trolleys in the diagram collide and join together and they move off together. And we need to calculate the velocity with which they move off. Now, in order to do this, we have to look at the momentum before and we have to look at the momentum after. So worth remembering that those momentums that we calculated in part 1 are the initial momentum, the momentum at the start before the collision. So let's now look at the initial momentum. So the momentum before the collision is going to be the sum of the momentum of trolley A before plus the sum of momentum of trolley B before. These numbers we've already calculated from part 2, so we just add together 16 plus 2, and we find out that the momentum before the collision was 18 kilogram meters per second. Now let's look at the momentum after the collision. So the momentum after the collision is going to be the momentum due to trolley A afterwards, plus the momentum due to trolley B afterwards. Now, crucially, in this example, the two trolleys stick together. That means they're going to be travelling at the same velocity because they essentially become one object that has the mass of both of them. So I'm going to write the momentum after as the mass of A plus the mass of B. That's in brackets, and all of that is multiplied by V. Note how I'm using the symbol V here because it's the final velocity. Now, we know that the mass of trolley A and the mass of trolley B are 8 and 4 respectively. And so we know that our momentum after is therefore going to be 12 times by V, where V is the final velocity we are trying to work out. Now we can use our principle of conservation of momentum. We know the total momentum before must be equal to the total momentum after. Well, the total momentum before is 18 kilogram meters per second, and the total momentum after we know is 12V. So we can substitute in those numbers, and then we can transform the equation to make V the subject, and we find that the final velocity after is 1.5 meters per second. Note that the fact that this is a positive value means the trolleys are moving in the same direction as they were at the start. Let's now have a look at an example together. The figure shows a skateboarder jumping forwards off their skateboard. The skateboard is stationary at the moment the skateboarder jumps. The mass of the skateboard is 1.8 kilograms and the mass of the skateboarder is 42 kilograms. Calculate the velocity at which the skateboard moves backwards if the skateboarder jumps forward at a velocity of 0.3 meters per second. In this, we are going to call the skateboard B and the skateboarder A. We are told the skateboard is stationary at the moment the skateboarder jumps. This means that at the start, the skateboarder and the skateboard are both stationary, meaning their velocity is 0. So, as before, let's calculate the momentum before the event. The momentum before the event will be the sum of the momentum of the person, which you've called A, and the sum of the momentum of the skateboard, which you've called B. Since their initial velocity is both 0, the mass times by the velocity will also be 0. So the total momentum before the event is very simply 0 kilograms meters per second. Let's now have a look at the momentum after the event. So the momentum after the event is going to be the sum of the momentum afterwards due to the person and the sum of the momentum afterwards due to the skateboard. Note how they don't move off together this time. We can see the skateboarder jumps forward, but the skateboard moves backwards, and that's why we have these as separate calculations as opposed to the previous example. So the momentum after the event, well, we are told that the skateboarder has a mass of 42 kilograms and they move forward at a velocity of 0.3 meters per second. We also know the mass of the skateboard is 1.8 kilograms, but we don't know its velocity. That's what we're trying to find out. So we're going to leave that as VB. So we can simplify this and we can see the momentum after is 12.6 plus 1.8 VB. We can then use the fact that we know the total momentum before is equal to the total momentum after, and we know the total momentum before is 0 and the total momentum after is 12.6 plus 1.8 VB. Can you now pause this video and complete the rest of the calculation? Hopefully you've now got your lines of working. We are now going to self-assess our work. So the total momentum before equals the total momentum after. This means you should have written down that 0 is equal to 12.6 plus 1.8 VB. We can then minus 12.6 from both sides to get minus 12.6 is equal to 1.8 VB. To get VB by itself, we then divide both sides by 1.8. Note how the answer here is negative. That is crucial. If the forwards direction is positive 0.3 meters per second, then the fact the skateboard moved backwards means we expect that negative sign. That negative sign shows us the velocity is in the opposite direction. So we could write this as the velocity of the skateboard is 7 meters per second backwards. So can you now have a go by yourselves at this final example? And self-assessing your work. In my example, I have called the car A and the van B, but you might have used different ones in your answers. The momentum before the event we do by looking at the initial conditions. Those are the ones on the left-hand side of that diagram. And the momentum after the event, we look at the right-hand side of that diagram. Again, we don't know the velocity of the lorry. That's what we're trying to work out. We must have written down that the total momentum before equals the total momentum after. So therefore we get 12,000 is equal to 2,400 plus 3,200 VB. And then we rearrange to make VB the subject, and we end up with 3 meters per second. This tells us that the van moves at a velocity of 3 meters per second forward, i.e. in the same direction as the car.